Alright, let's go. Number 10. The Wheeler-DeWitt equation. In the mid-1960s, Bryce DeWitt was working at the University of North Carolina on a piece of technical bookkeeping. Paul Dirac had laid out a recipe for quantizing systems with constraints. DeWitt wanted to apply that recipe to Einstein's general relativity and get the gravitational version of the Schrödinger equation. That was the whole ambition. A tidier equation for a field that already had one. Here is what he expected to find. In ordinary quantum mechanics, the Schrödinger equation describes how a wave function changes as time passes. Time sits on one side as a parameter you feed in from outside, an external clock, ticking independently of whatever the system is doing. Every physicist in 1965 assumed the quantum theory of gravity would look the same, with a more complicated Hamiltonian bolted on. The time term did not survive the calculation. It did not become small. It did not become approximate. It vanished, because in general relativity the total Hamiltonian is itself a constraint that has to equal zero. What was left red, acting on T psi, equals zero. The wave function of the universe does not evolve. DeWitt published it in Physical Review, Volume 160, in 1967, in a paper titled Quantum Theory of Gravity. The canonical theory. By his own account, he had shown the result to John Wheeler 2 years earlier at the Raleigh-Durham Airport, and Wheeler was delighted by it in a way DeWitt found difficult to share. DeWitt spent decades calling it that damned equation. For years afterwards, each man referred to it as the other one's equation. Attempts to put the time back have been running for 50 years. You can pick a physical variable inside the universe and promote it to a clock, a scalar matter field, or the York time built from extrinsic curvature. Carol Kucha and Chris Isham cataloged these strategies in review papers in 1991 and 1992, and both concluded the same thing. Different clock choices produce quantum theories that are not equivalent to each other. Tom Banks argued in 1985 that time re-emerges in a semi-classical approximation, which works, but only by assuming in advance the classical background it was supposed to derive. Generic spacetimes admit no global time function at all, and nobody has produced a positive definite inner product for the resulting states, which means the theory still has no agreed way to compute a probability. Kucha gave the sharpest version of the failure a name, the multiple choice problem, and 6 decades on, the count of strategies that survive it is 0. You have organized your entire life around a quantity that does not appear in the best candidate equation for the universe as a whole. Your salary is time-indexed. Your medications are time-indexed. Your body is running a chemical countdown you did not set. The single most load-bearing structure in your day is the one the equation has no slot for. If the master equation of the universe contains no time variable, what exactly have you been counting since the day you were born? That question sat unanswered for 16 years, until 2 physicists found the loophole. Number 9. Evolution without evolution. In the early 1980s, Don Page was working on quantum cosmology, and William Wooters was working on the foundations of quantum information, the same period in which Wooters and Wojciech Zurek proved you cannot clone an unknown quantum state. Their shared problem was mundane and specific. If the universe is described by a frozen state, and the equation says nothing changes, how do you write down anything at all that a physicist inside the universe could measure? The standard reasoning was clean. An observable that commutes with the Hamiltonian is a constant of motion. If the Hamiltonian annihilates the state, every observable of the whole universe is a constant of motion. Nothing happens, ever, anywhere, to anything. That is not a subtle prediction. That is the flat contradiction of every experience anyone has ever had. Page and Wooters split the universe in 2. One piece is a clock. Everything else is the rest. Entangle them. Now ask a conditional question. What does the rest look like, given that the clock reads a particular value? And the answers change from one clock reading to the next, while the total state sits perfectly still. They published it in Physical Review D, Volume 27, page 28A5, in 1983, under the title Evolution Without Evolution, Dynamics Described by Stationary Observables. For 30 years it was treated as a formal curiosity. Then, in 2013, Ekaterina Moreva. Working with Marco Genovesi's group at Italy's National Metrology Institute in Turin alongside Vittorio Giovanetti and Lorenzo Mocconi, built a two-photon version on an optical bench. The polarization of one photon served as the clock. The result appeared in Physical Review A, Volume 89, Article 052122 in 2014. An observer restricted to the internal photon measured a system evolving. An observer measuring the pair globally found a state that had not changed. The framework has been attacked steadily since. Kuch's 1992 critique showed that the conditional probability construction gives the wrong answers for measurements made at two different times, and that naive versions violate the constraint they were built to respect. Giovanetti, Lloyd, and McCone rebuilt the formalism with a properly defined clock Hilbert space in Physical Review D, Volume 92 in 2015, which repaired part of the damage. But any real clock has finite energy and finite dimension, and finite clocks give smeared, imperfect time. Worse, nothing in the theory tells you which subsystem is the clock. You choose. And a different choice gives a different history. A further complaint has never been answered at all. The construction reproduces the appearance of change and says nothing about why change should run one way. It delivers an ordering without a direction, which is half of what anyone wanted. Every cell in your body is entangled with its surroundings. On this reading, the reason you experience one moment following another is not that moments follow each other, but that you are correlated with something you are using, unconsciously, as a dial. If time is a correlation between you and the rest of the universe, what is happening to the universe that is not correlated with you? Correlation is strange enough. The next result is 100 years old and has never been contested. Number 8. The Relativity of Simultaneity. Albert Einstein spent 1902 to 1909 as a technical examiner in the Swiss Patent Office in Bern. A large share of the applications crossing his desk concerned electrical clock coordination, the practical, tedious, deeply commercial problem of making the clocks in one town agree with the clocks in another town over a telegraph wire. Historian Peter Gallison has traced the overlap in detail. Einstein's day job was clock synchronization. The assumption he was working against was Newton's, and it is the assumption you are still running. There is a fact about whether two distant events happen at the same moment. The universe has a present tense. Everything that exists, exists now, and now is the same now everywhere. Einstein showed the question has no answer. Two observers in relative motion slice the universe into moments along different planes. Both slices are legitimate. Both observers are correct. The disagreement is not about measurement error or signal delay. It is about which events are simultaneous, and there is no fact of the matter to appeal to. The result is in On the Electrodynamics of Moving Bodies, Annalen der Physik, Volume 17, 1905. Roger Penrose gave the sharpest illustration of it in his 1989 book, The Emperor's New Mind. Two people pass each other on a pavement, walking in opposite directions at about a meter per second. The offset in simultaneity scales with distance, so it is nothing locally. But apply it to the Andromeda Galaxy, 2.5 million light-years away, and the two pedestrians' definitions of right now at Andromeda differ by roughly 3 days. If an invasion fleet launched there this week, one pedestrian's present already contains the launch and the other's does not. And neither of them is wrong. Philosophers have spent 60 years trying to rescue the present tense from this. Karel Reitdijk in 1966 and Hilary Putnam in 1967 both argued the escape is impossible, and that relativity forces a four-dimensional block. The counter-proposals each cost something. You can posit a hidden preferred frame in the style of Lorentz, which is internally consistent and, by construction, undetectable in principle. Howard Stein proposed in 1968 restricting the present to a single-point event, at which price your present contains you and nothing else. Kit Fine's Fragmentalism, published in 2005, keeps a real present by shattering reality into fragments that never combine into one world. The cosmic microwave background does define a rest frame. But that is a fact about how matter happens to be distributed, and it leaves the light cone structure of the theory untouched. A century of proposals, and the honest scoreboard reads, consistent options exist, and every one of them is either untestable in principle or purchased by breaking something else. The word now, applied to anything further away than the room you are sitting in, does not refer. There is no shared instant containing you and a person on Mars. The moment you are having is a local convention, and it stops working at any distance that matters. If there is no universal present, in what sense does the present moment exist at all? The next entry attacks the direction, not the moment. Number 7. The arrow is only statistics. Ludwig Boltzmann was trying to solve a problem in engineering adjacent physics. Why does a gas released into a box spread out and stay spread out? He wanted to derive that behavior from the mechanics of colliding particles, and in 1872 he produced the H theorem, which appeared to show that a quantity related to entropy can only increase. The mechanics he started from is time-symmetric. Newton's equations, Maxwell's equations, the Schrödinger equation, take any solution, reverse the sign of the time coordinate, and you get another valid solution. At the level of the fundamental laws, a film of a molecular collision run backwards shows nothing illegal. There is no built-in forward. Joseph Loschmidt pointed out in 1876 that you cannot derive an asymmetric conclusion from symmetric premises. Ernst Zermelo added in 1896 that Poincare recurrence guarantees the gas will eventually unspread on its own. One honest caveat, because this audience will find it otherwise. The laws are not perfectly time-symmetric. James Christensen, James Cronin, Val Fitch, and Ren Turley found CP violation in neutral kaon decay in 1964, reported in Physical Review Letters Volume 13, in effect at the level of about 2 decays in 1,000. Direct time reversal violation was observed by the Barbour collaboration in 2012, published in Physical Review Letters Volume 109, Article 211801 at 14 sigma. Real, confirmed, and completely irrelevant to your coffee going cold. That asymmetry is a rounding error in the weak interaction and does nothing to explain thermodynamics. Which leaves the explanations of the arrow, all of which have holes. Coarse graining derives entropy increase from grouping microstates into macrostates, but somebody has to choose the grouping. So the arrow leaks in from the observer. The past hypothesis, named by David Albert in his 2000 book Time and Chance, simply posits an extraordinarily low entropy initial condition. Penrose put the required precision at 1 part in 10 to the power 10 to the power 123, and posits is the operative verb. Boltzmann's own fallback, that we live inside a giant fluctuation, dies on the Boltzmann brain problem. A fluctuation producing a single diluted brain is overwhelmingly more probable than one producing a galaxy. Inflation is often cited as the fix, but Penrose has argued for decades that inflation requires a low entropy starting point of its own, which relocates the mystery rather than removing it. Decoherence supplies a very clean arrow for quantum systems, and then quietly assumes an initial unentangled state to get started. Every route ends at the same place, an unexplained condition at one end of the universe. The difference between the fixed past you remember and the open future you are anxious about is, on the current best account, a fact about counting. It is a ratio of possible arrangements, not a law. An accounting result. If the direction of time is bookkeeping rather than physics, why does it feel like the most solid thing about being alive? Statistics can be argued with. The next experiment was run in a laboratory. Number 6. The Delayed Choice Quantum Eraser. In 1982, Marlon Scully and Kai Dr. Hell were chasing a narrow technical question in quantum optics. The textbook explanation for why which path information destroys an interference pattern was mechanical disturbance. You bounce something off the particle, you kick it, the pattern smears. Scully and Doctoral asked whether the information itself was doing the work. Their proposal appeared in Physical Review A, Volume 25, page 2208. The prediction following John Wheeler's delayed choice argument from 1978 was that the timing should not matter. If information is what governs interference, then destroying that information after the particle has already been detected should still restore the pattern. Wheeler expected this to sound absurd enough to reveal a flaw. It was built. It worked. Yoon Ho Kim, Rong Yu, Sergei Kulik, Yanhua Shi, and Scully published the experiment in Physical Review Letters, Volume 84, page 1, in the year 2000. A crystal splits each photon into an entangled pair. The signal photon hits its detector first. Its partner travels an extra optical path of roughly 2.5 meters, about 8 nanoseconds of delay, before its own path information is either preserved or erased. Sort the already recorded signal detections according to what happened to the partner afterwards. And one subset shows interference fringes while the other does not. Now the part most videos get wrong, and this audience is caught before. The raw signal pattern shows no interference at any point, ever, regardless of what is done downstream. The fringes appear only inside subsets selected by the later measurement, coincidence counting. Nothing propagates backwards, and no signal can be sent to the past. Ruth Kastner made the case bluntly in Foundations of Physics in 2019, arguing the experiment neither erases nor delays anything. Retrocausal interpretations, including John Kramer's transactional account and Hu Price's work, remain live but have produced no test that distinguishes them from standard quantum mechanics. Superdeterminism escapes the puzzle by denying that experimenters can choose settings freely, which most physicists regard as a higher price than the problem. Jean-François Roche Group closed the original delayed choice version with a fast random switch in Science, Volume 315 in 2007, and the results match textbook quantum mechanics exactly. Many Worlds absorbs the result without strain and hands you a branch structure in which the past is relative to which branch you find yourself on, which is not obviously an improvement. And the orthodox reading, that this is ordinary post-selection and nothing more, is correct and complete, and still leaves you describing a correlation whose two halves are separated in time with no story about how they got connected. What survives, after all the debunking, is uncomfortable in a specific way. The correlation is real. It links a detection event to a choice made after it. No interpretation explains it with a mechanism that runs in temporal order, and the experiment has been repeated for 1/4 of a century without that changing. If a correlation exists between two events and no time-ordered mechanism connects them, what is the ordering doing there? Some physicists have concluded the ordering comes from what we do not know. Number 5. The thermal time hypothesis. Through the 1970s, Elaine Kahns was classifying von Neumann algebras, abstract operator algebra, about as far from cosmology as mathematics gets. Building on the Tomita-Takasaki theorem, he proved something peculiar in 1973. A state on one of these algebras generates its own one-parameter flow, and that flow is canonical, fixed by the algebra itself up to an inner transformation. The mathematics produces a preferred direction of change out of nothing but the structure. The physics problem waiting for it was a deadlock. Statistical mechanics needs a Hamiltonian to define equilibrium, and a Hamiltonian requires a time variable. General relativity refuses to supply one. Every attempt to write down the statistical mechanics of a gravitational field ran into the same wall. Carlo Rovelli saw the flow and read it in reverse. Instead of using time to define equilibrium, use the equilibrium state to define time. The state you are in generates the flow. Rovelli and Kahns published this in Classical and Quantum Gravity, Volume 11, page 2899, in 1994, following Rovelli's own paper from 1993. Time, on this account, is a consequence of describing a system by a statistical state rather than by its exact microscopic configuration. There is one case where the answer can be checked against known physics. The Bissognano-Wichmann theorem from 1975 and 1976 shows that for the Minkowski vacuum restricted to an accelerating observer's wedge, the modular flow is exactly a Lorentz boost, reproducing the Unruh temperature derived independently in 1976. In the single case where we can verify it, the mathematics returns the right physical clock. Everywhere else, it is unconstrained. For a generic state, the thermal flow corresponds to no clock anyone can build. The construction hands you a flow, but not a direction. So the arrow of time has to be imported from somewhere else anyway. It requires a specific class of algebra which is natural in quantum field theory and unproven in quantum gravity. And in more than 30 years, no one has proposed an experiment that would confirm or refute it, which for a hypothesis about the origin of time is a serious mark against it. The claim, stripped of the mathematics, is that time is generated by your ignorance of microscopic detail. A being that knew the exact position and momentum of every particle in this room would not experience a slow clock or a fast one. It would have no clock at all. On that reading, the reason you are aging is that you cannot see well enough. If time exists because we are ignorant, what does a complete description of the universe look like from inside? Ignorance is one candidate origin. Discreteness is another. Number 4. The Big Bounce. Abhay Ashtakar's 1986 work was a change of variables. General relativity written in Einstein's original terms produces constraint equations that are non-polynomial and effectively impossible to quantize. Ashtakar found a reformulation in which the constraints become polynomial and tractable. This was a technical convenience, published to make an existing calculation possible rather than to say anything about the beginning of the universe. What the existing theory said about the beginning was unambiguous. Wind general relativity backwards and the curvature diverges. Density goes to infinity, the equations produce meaningless output, and the theory declares its own failure at a point roughly 13.8 billion years ago. Everyone agreed this was where physics stopped. Quantize it with the new variables, and the equations do not stop. The density climbs, reaches a maximum, and turns over. Abhay Ashtakar, Tomasz Pawlowski, and Parampreet Singh published this in Physical Review Letters, Volume 96, Article 14131 in 2006, in a paper called Quantum Nature of the Big Bang. The turnover occurs at a critical density of about 0.41 times the Planck density, on the order of 10 to the 96th kilograms per cubic meter. Underneath it sits the discreteness result of Carlo Rovelli and Lee Smolin from Nuclear Physics B, Volume 442 in 1995, in which area comes in quantized units of about 10 to the minus 70 square meters. And in the spin network formulation, evolution is not a continuous parameter at all. It is a sequence of discrete transitions from one combinatorial graph to another. There is no smooth time to divide by, which is where the strongest version of the claim lives. The universe did not begin, not because it is eternal, but because a beginning requires a moment before which there was nothing. And there was no moment. The theory has not earned that sentence yet. The bounce comes from symmetry-reduced models, where the universe is simplified to a handful of variables before quantization, and nobody has shown that reducing first and quantizing gives the same answer as quantizing the full theory. Thomas Tiemann's construction of the Hamiltonian constraint in 1996 admits multiple inequivalent versions with no principle selecting between them. The semi-classical limit, recovering ordinary general relativity from the discrete structure, has never been fully demonstrated, which is the criticism string theorists have pressed hardest. The Amirzi parameter, which sets the scale of the whole discrete structure, is fixed after the fact by matching black hole entropy, a calculation that only works because you already knew the answer. And the predicted imprints on the microwave background have not been detected at the sensitivity reached so far, which means the bounce currently explains an observation nobody has made. The clean number you have heard your whole life, 13,008 billion years, the age of everything, may not be an age. It may be the distance to a bounce, on the far side of which the question has no meaning. If the beginning of time is a boundary in a theory rather than an event, what were you told happened? Even that number is now in dispute, for a much more ordinary reason. Number 3. The Hubble Tension. Two teams were doing routine parameter estimation. Adam Riess's ZEUS collaboration was calibrating C-feed variable stars in nearby galaxies to anchor the distance ladder out to Type 1a supernovae. The Planck collaboration was fitting the temperature and polarization spectrum of the cosmic microwave background. Neither team was hunting an anomaly. Both were tightening error bars on a number astronomers had been refining since the 1920s. The expectation is the least controversial in cosmology. Measure the expansion rate from the early universe and measure it from the local universe. And the two must converge, because they are measurements of the same universe. For decades, the error bars were wide enough that they overlapped and nobody worried. Then the error bars shrank, and the numbers did not move together. The Planck collaboration's final analysis gives a Hubble constant of 67.4 plus or minus 0.5 kilometers per second per megaparsec. Rios and colleagues, publishing in Astrophysical Journal Letters Volume 934 in 2022, give 73.04 plus or minus 1. 0.4 from the distance ladder. That is an 8% gap, and taken at face value it stands at roughly 5 sigma, the threshold physics uses to declare a discovery. The James Webb Space Telescope was expected to break the deadlock by exposing errors in the Cepheid photometry. It confirmed the photometry instead. Everything proposed to close it has cost more than it saved. Cepheid crowding in dense fields was the leading suspect and has been checked. The tip of the red giant branch gives intermediate values, and Wendy Friedman's Chicago Carnegie program argues that once the drift in systematics is honestly folded in, the real tension may sit nearer 3 sigma than 5. A serious descent, not a fringe one. A large local underdensity would bias the nearby measurement, but the observed void is not deep enough. Early dark energy shrinks the sound horizon and lifts the inferred value, at the cost of worsening agreement with Big Bang nucleosynthesis and with matter clustering. DESI's second data release in 2025 does prefer evolving dark energy over a cosmological constant at 3 to 4 sigma, depending on the dataset combination, and that preference pushes the inferred expansion rate down, not up. Additional light relic species raise it, at the price of a conflict with the primordial helium abundance. Gravitational wave sirens and lensed quasar time delays were both expected to referee the dispute, and have so far landed between the two camps with error bars too wide to convict either. The age of the universe is calculated from this number. At 67, you get 13.8 billion years. At 73, you get closer to 12.8. The gap is 1 billion years, and it depends entirely on which method you trust. Not the age of a distant object, the age of everything, including the atoms in your hand. If 2 correct measurements give the universe 2 different ages, what time is it? One physicist looked at all of this and drew the obvious conclusion. Number 2. Platonia. Julian Barbour left mainstream academia in the 1960s and supported himself for decades translating Russian scientific journals, because the problem he wanted to work on was not fundable. The problem was Ernst Mach's, can you build a physics using only the relative positions of things, with no absolute space and no absolute time in the background at all? It was a question about tidying up foundations, not about abolishing anything. Standard mechanics answers by giving you a configuration and a timestamp. Positions plus a clock reading. The clock reading is separate, external, and does the work of ordering everything. Barbour deleted the clock and found the physics still ran. Working with Bruno Bertotti in a paper published in the Proceedings of the Royal Society A, volume 382, in 1982 he constructed a relational dynamics using a procedure called best matching, in which duration is not an input. Duration is computed from how much the configuration changed. Time becomes a derived measure of difference between arrangements, and the arrangements themselves are the only things that exist. Barbour called that space of arrangements Platonia, and set it out for general readers in The End of Time in 1999. Every arrangement is static. Certain arrangements, he calls them time capsules, contain internal structures that look like records of other arrangements. Those are the ones that feel like a moment inside a history. The gap in the argument is the one Barbour himself has always named. He conjectures that the wave function of the universe concentrates on time capsules, which is what makes the world look ordered rather than chaotic. He never proved it. The static universe framework he builds on inherits every unresolved problem from entry number 10, including the missing inner product. Critics have pointed out that records already presuppose the ordering they were introduced to explain, which risks running in a circle. And in 2014, in Physical Review Letters Volume 113, Article 181101, Barbour published with Tim Kozlowski and Flavio Mercati a result showing that a relational system of gravitating particles has a complexity that grows in both directions from a central state. An arrow of time appearing inside a framework built to have none. The structure of the claim is worth sitting with for a moment. Every memory you have of your childhood is physically present in this instant, encoded in the arrangement of tissue behind your eyes right now. The photograph on your wall is here, the scar is here. The feeling of having come from somewhere is a property of the present configuration, complete and self-contained, and it would be exactly the same if nothing had ever preceded it. If this instant contains its own evidence of a past, what work is the past still doing? Put every entry together and the conclusion writes itself. Number 1. You have never moved. Benjamin Libet's original work was clinical, not philosophical. He was studying patients undergoing brain surgery under local anesthesia, stimulating the cortex directly to map sensation, and trying to determine how much cortical activity is required before a person reports feeling something. The assumption running underneath all perception research at the time was that consciousness is roughly live. Signal arrives, brain processes it, you experience it, with a short and uninteresting lag. The lag was half a second, and the experience was dated backwards. Libet and colleagues published this in Brain, Volume 102 in 1979, in a paper on the subjective referral of the timing of conscious experience. Around 500 milliseconds of cortical activity were needed for awareness, yet subjects placed the sensation at the moment the signal first reached the cortex, a timestamp assigned retroactively to an event whose processing had not finished. Paul Kohlers and Michael von Gernau found the same construction in the color Phi phenomenon in vision research in 1976, where a dot appears to change color partway through a motion that never occurred, meaning the switch is inserted before the brain has seen the second dot. Frank Geldard and Carl Sherrick's cutaneous rabbit in Science Volume 178 in 1972. Does the same with touch. Taps at the wrist are felt marching up the forearm toward a location that has not been tapped yet. Libet's methodology has been contested for 40 years, and the backward referral interpretation is not settled. Daniel Dennett and Marcel Kinsborn argued in 1992 in Behavioral and Brain Sciences Volume 15 that these results have no fact of the matter at all. That asking whether the brain revised the experience or revised the memory of it is a question with no possible experimental answer. That is not a solution. It is a demonstration that the ordering of events inside your own head is not a well-defined quantity. Now stack the list. No time variable in the master equation. No universal present. No fundamental arrow. Time recoverable from entanglement, from ignorance, from discrete transitions. 2 expansion rates giving 2 different ages. A relational physics that runs without duration, and a brain that assembles the present moment retrospectively out of material that arrived late. Nothing on that list produced a moving now. Einstein wrote to Michel Besso's family in 1955 that for physicists like him, the distinction between past, present, and future is only a stubbornly persistent illusion. You did not travel from your childhood to this sentence. You are spread across the whole of it, entire, already, and the sensation of passage is a 4-dimensional object reading itself one slice at a time. If you are not moving through time, what is the thing that feels like moving? Every entry on this list came from inside our most successful theories, not from their ragged edges. Relativity is the most precisely confirmed framework in the history of science, and it deletes the universal present. Quantum gravity's cleanest equation deletes the time variable outright. Thermodynamics gives the arrow and admits it is counting. The pattern is not that we lack data about time. The pattern is that every theory that works refuses to contain it, and we keep putting it back by hand because the alternative is unbearable. The universe is not confused about what time it is. We are the ones who need there to be an answer. If you want to see more videos like this, click the video on screen now.